Microwave Observations Group. I'm currently a UMAP SAT Fellow focusing on microwave images. And today I'm going to talk to you about the use of interface observations in a coupled atmosphere-ocean system. So what do we really mean by this? So interface observations are observations that are sensitive to more than one parameter in the Earth system model. So in the case that we're talking about here, we're really talking about skin temperature increments, or skin temperature and its relation to the sea surface temperature. So here I'm showing a very simplified diagram, which basically is trying to say that if you can derive information in the atmospheric body far system, which can then be directly added to the ocean system to try and improve the ocean. So the case study that I'm looking at, as I just mentioned, is the skin temperature increments. These can be derived from infrared and microwave observations, as I'll discuss in a minute. And in the system that we're looking at, we just add them as if they were errors in the sea surface temperature into NemoVar. I'll go into the method of the coupled system a lot more in a few minutes. But firstly, I want to talk to you more about these skin temperature increments, why they are important, and the results that we've got for those using the microwave. So firstly, a bit on the motivation of this. This has already been undertaken for infrared observations for Chris and ISDA a few years ago. And it was found that these really improve the system. So here on this side, we can see that the fit to independent ocean observations really improves with the implementation of this coupled system. So we go from a control here, the red line, to the improved system in the black line. And you can see that in sort of the first half meter of the ocean, we're getting these improvements. In addition, it's also improving the atmospheric side. So here we're showing the background standard deviation normalized between the two experiments, with the control being the 100%, and the black line shown here being the change in the standard deviation of the departures. And these are all for ISDA. So this large peak that you can see, which is going up to almost 8% in a couple of cases, are really surface sensitive observations. So this is showing that if you use these interface observations in a coupled system, you can really see an improvement in the atmosphere as well as the fit to ocean observations. So this is a really good motivation to try it out for different observations. So as I said, I work with microwave images, so I'm looking at how we can use these for the microwave. And one of our key motivations here is the spatial and temporal coverage that we can get from microwave observations compared to infrared. So infrared has to be subject to cloud screening because it can't be modelled under all sky conditions, whereas microwave, or it can be, but it's not yet. Microwave can be, or is implemented in the ECMWF system under all sky conditions and has been for some time. So this really gives us a much stronger coverage. In addition to this, we can derive information about the surface parameters in the microwave at all super ob locations. Currently in the atmospheric 4D VAR, we only use 1 in 8 super ob observations because of correlation of errors. But for AMSR2, for sea surface temperature and skin temperature work, we can use a lot more information. So this really gives us like a strong motivation to try this out for the microwave to see the improvements that we can get using this information. So taking a step back for a moment, we need to have a look at why skin temperature is important. Why does it need to be modeled correctly, and the impact that it can have on the system? So here I'm just showing a very basic schematic, which doesn't include everything, of how skin temperature is used in the ECMWF system. So you have your two input SST products. So we take in information from ISDA and Ocean 5. This is in the current operational configuration, depending on the latitude of the observation that we're looking at. These are then parameterized to create skin temperature. So this is a cool skin parameterization and warm layer parameterization, and this kind of gives you your skin temperature, which has a diurnal cycle in it. Now, this skin temperature and the ocean, the SST measurements are all used in the model, and I haven't shown a nice big arrow showing that here, but for simplification, I want to concentrate on how it's used in the observation operator to provide simulated radiances. So, as everyone knows, these simulated radiances and the observations go into the departures, which are integral to the DA system. However, if we have any errors in these initial input SST products or the skin temperature parameterization, these can result in a direct error in the simulated radiances. So I did a very small study where I just changed the input skin temperature by 0.2 Kelvin, just to see what would happen to our simulated radiances. So here on the y-axis, I'm showing the difference in the simulated radiances between a case where I've added this 0.2 Kelvin and a case where I haven't. And on the x-axis, we're showing the model skin temperature. So there are a few things to note from this diagram. Firstly, everything has a dependence on the model skin temperature. Everything's changing across that range. Secondly, and quite expectedly, we have a larger dependence of the surface sensitive channels. So here this is 6 gigahertz and 10 gigahertz on the input skin temperature. And thirdly, these are not insignificant changes. So this for 6 gigahertz goes up to about 0.14-ish change in the simulated temperatures. And this, the standard deviation of the first guess departures at 6 gigahertz is only about 0.7, so that's actually quite a significant jump. So if we can eliminate or at least address some of the errors in the input skin temperature, we would improve our first guess departures and hence the overall system. So without even considering going into the coupled system, there's a strong motivation to try and improve the skin temperature in the system already. So another motivation for using microwave is that we do have surface sensitive channels. So it's well known that at 6 gigahertz, you get a peak of sensitivity to SST. And this is a figure from Lise Klik's paper from 2021 relating to SIMA, the upcoming SIMA mission. So here in orange, we can see the SST peaks. And in the tropics, we really get this great sensitivity at 6 gigahertz, and it's still there at 10.65 gigahertz. So it's really important to be able to exploit this information. However, these channels have never before been used in the ECMWF IFS. So there's been some work that's had to go on for that. Just to note, independently, but not shown here, we have also tried out the skin temperature increments without 6 and 10, and we see that the magnitude of the increments isn't so strong, and the geographical features, which I will show in a few slides' time, don't come out. So this is really a strong motivation to be using these lower frequency channels that have surface sensitivity. However, as I said, they have their own issues. So I've spent quite a lot of time the last year or so looking at the quality control of 6 and 10 gigahertz. One thing I haven't shown here is that we've had to adapt our coastline screening because of the larger footprint of 6 gigahertz. But something that was a little unexpected, although has been recorded in the literature before in a few papers, is sunglint. It's just how strong this effect is. So at the top here, I'm showing first guess departures on this side for MSR2 and here for GMI. And you can see that there are these large streaks. And if we look at glint calculations, so this is the glint between the Sun and AMSR2 and the Sun and GMI. This dark blue color is showing 0 glint. So this is really aligning with the high first guess departures we see here. And if I haven't shown it here, but if I plot first guess departures versus glint angle, we come up with a very nice curve, which shows that these are really in exactly the same place. So this has very simply been screened out in the work that I've done here. Next, we come on to a large problem with the lower frequency channels, which is radio frequency interference. So this just shows the orbits over Europe for MSR2 for a single day. And we can see that there are these large kind of scar patterns of high first guess departures around the UK and Spain and around the bottom of Italy. And we are certain these are from these are reflected from satellite and geostationary orbit. So what I've done here is I've placed a theoretical satellite at 1 degree spacings around the world, and I have calculated the glint angle. For any glint angles under 3 degrees, I've then generated the mean first guess departure from this exact geographical area that we see here. And then I've put these into this nice little plot, which you can see on this side, to show that we see peaks of the first guess departures at which correspond with a satellite in orbit at these particular longitudes. So if we then look at this in a bit more detail, we can see that these areas are the areas that are corresponding to a satellite placed at 13 east. These are this area to the south of Spain, or sorry, to the west south of Spain, is corresponding to a satellite at 30 west, and this area here is corresponding to a satellite at 38 east. So this kind of simplified method allows us to identify where these reflected direct broadcast satellite signals are coming from, and that allows us to then put a screening method into the IFS based on this. Work is still ongoing to look at some areas over America at the moment, and also to look at GMI. This is all shown for AMSR2. Okay, so now we move on to the skin temperature increments, and I must apologise, the RFI screening hasn't been implemented in this plot, but you can actually see the effect of it quite clearly, which demonstrates nicely that this quality control work that I've been doing is really important to get this system working well. So there is a lot of information going on this plot, but there's one thing that I really want to talk about, and this is the cooling of the cold tongue and the effect on the western boundary currents that we see coming off of Africa and South America here. Now, the reason that these particular increments out of everything else that we see is important is because these have there's a known deficiency of these in the OFStream 5 input product. So we know that this change is real and that it's
3 minutes, Tracy.
Oh, right, okay, and that it's yeah, it's a really important signal. So this gives us confidence that our skin temperature increments are working well. So let's move on quickly past the forecast scores a bit. We're limited on time, but here we have an apparent improvement in the humidity, which is also in the temperature when we look at the impact of including the skin temperature in 6 and 10 gigahertz. However, we're not sure if this is actually real, because we also see this effect in independent observation. So this is the change in the standard deviation of ISDA departures in the tropics. And we see that there's an improvement in the surface sensitive channels. However, in the upper troposphere humidity channels, we see that there's a degradation. So this is something we have to investigate as we go forward. So now moving on to the coupled system, I just want to show you the methodology and then one slide on some preliminary results. So we have the coupled system, and this has inside it the atmospheric and the ocean model doing the variational simulation. These provide out of them analysis of various parameters, and then these are pushed back into the next cycle through this route here. Apart from for the ocean where things are coming from the outside. So here is the coupled ocean model that we've been talking about. This is forced by in situ SST observations in the first trajectory and then in the subsequent trajectories. And this is where the increments that we've been talking about from satellites would come in. So after the first trajectory, we can use information that's come from the atmospheric 4D and put it directly into the ocean variational system. There is also an option to change this reinitialization and to have an analysis that comes straight from this. This is a long-term study because this would effectively allow the ocean to be only forced by like information from in situ and satellite. So moving on to my last slide, here we have the microwave. We've implemented the microwave observations into the coupled system. And this is just a very preliminary result based on 1 month of data. And we already see there are quite significant improvements in the first half meter of the ocean. So this line here is showing a statistically significant improvement. This is a really nice result to start with, but we are in the process of doing a lot of different tweaking methods to understand how this can change and its sensitivities, etc. I do have a summary slide, so just to reiterate, 6 and 10 have been included for the first time with robust quality control implemented. The skin temperature increments are now generated for microwave observations, and these have been used in the coupled system, which is currently being tested. So that's the end. Thank you.
Thank you very much, Tracy. We have time for a question or two. So thank you to Bruce Ingleby for your question. I'll read it out. The interference or glint from geostationary satellites, are they breaking the rules? I presume he's talking about the sort of regulation. And there is yes, sorry, go ahead. Yeah, so are they breaking the rules, and is there anything that can be done about this apart from screening?
So to answer the second question first, no, I think we have to screen out these observations. They're so affected by it. And actually, it's quite a large area we have to screen out. The threshold at which we start the screening, it can be up to like 15 degrees at the glint angle, and this does take out quite a lot of information. I can't really answer about whether the rules are being broken or not, because I think there's an unfortunate combination of effects going on. For example, the satellites that I looked up at these longitudes, I mean, they are broadcasting near 10 gigahertz, but it's in H polarization, but there could be an effect with the H polarization on the ocean and depending on sort of the wind speeds and stuff. We don't know exactly how that might be affecting it. We also know that the 10.6 gigahertz band is quite small, and it is adjacent to this allowed broadcast band. There may be some overlap from either side, so it's not clear to say anyone is breaking the rules. I think we will see more keenly information, we'll get more information about this once we have other sensors in orbit with similar frequencies being measured.
Okay, thank you. Have we got time for another, perhaps a quick one from me actually? Is it possible that any adjustment to the skin temperature you make during the simulation, during the atmospheric simulation, could also be compensating for any errors in the forward model?
Yes, so that's something I've got to investigate in a lot more detail over the next couple of months. I think that we could be getting signal in there from lots of different things. So it's just trying to minimize that by tuning the sensitivity of it, so the errors, etc., associated with the skin temperature. I can't point to anything clear at the moment, but as I was showing, the impact on the forecast indicates that we're fit into the surface at the expense of other parts of the atmosphere. So yeah, I think the answer is it's definitely something that needs to be looked into in a lot of detail before we can make this operational.
Okay, well, thank you for interesting talk, Tracy.
Thanks.